Today we are going to talk about secure programming. We know that program has to be correct and the program has to be efficient. Over here, we are concerned about secure implementation of the programs. Last week we go through this particular access control model where a user of low privilege can indirectly access sensitive file through a bridge. The bridge have elevated privilege. Whatever operation issue or request issued by the bridge will be granted by the reference monitors. So if the bridge is buggy, contain bugs, potentially the user, the attacker, can access more than he's supposed to. And this, we call it privilege escalation attacks. You may think that the bridge is so important, then it will not contain bugs. Unfortunately, in reality, many programs are buggy. They are not implemented correctly, and it's different from the original intention, the intent of the programmer. Such bugs very often remain hidden because the program will function normally because as the condition that triggered the bugs rarely occur. However, a malicious attacker will actively search for the conditions and then intentionally trigger them. Okay. So, for example, the attacker may supply input in a form that is not anticipated by the programmer and then cause the process to access more resources, okay, or even crash the process. Okay, so that is the attacker, by fitting in carefully crafted input, he may compromise the execution integrity. Many such bugs are very simple, easy to correct when found, but the programs of complex systems are large, so making detection of such bugs are very challenging. There are many different types of bugs, and we try to organize them and classify them. But it's very difficult because many bugs are specific to the application and specific to that particular programs. A very well-known books that attempt to organize them is this one, a 24 Deadly Sins of Software Security. Okay. I believe this is free and then you can download from the internet. Let's look at the first examples, printf. Printf is a function in the C library for formatting output. Okay, let's look at these examples. To use printf in the program, we will write in this way, printf, and this is called a format and the parameters. So in this case, when these two parameters is supplied to the library call, the output will be this. This will be printed out. The value in temp is, and this is some control parameters, percentage. So it's percentage D, and this means that we will take this as and treat this as integer, print it out, and then print out a new line. So in this case, temp happened to be 100, so this will be printed out. So the percentage D indicate the type of variable. Okay, this is another examples. Okay, so when this is supplied to when these three parameters, 1, 2, 3, is supplied to the library call, the printf during execution time, during runtime will do this. Printf during runtime will scan this string starting from the left. So it started to print, display all this until it hit a percentage. Then because this is a percentage S, printf will interpret this as a string. So he will go to the next parameters and take the value of this, treat it as a string and print it out. Right. And now after that, he continue to print until it hit another percentage. And in this case, it's a percentage S. So printf will go to the next parameters, treat this as a string and print it out. What if only one parameter is supplied? Like in this case, printf hello world will be displayed. Now, the interesting part is this. Okay, what if the first parameter, the string, indicate that there is integer here, and yet there's no second parameters? What will happen? The printf library during runtime will still continue to print. Okay, you will started to interpret this, print out hello world, and he saw a percentage. What if counter a percentage? During runtime, he will go to pick up, look at the location of the second parameters, okay, and pick out the value and print it out. If there's no second parameter here, he will go to the supposing location of the second parameter, take it and print it. So for example, if let's visualize this as a memory location, the memory, and this is the place where it's supposed to store the second parameters. And over here, the value happened to be 15. Then what will be printed out will be hello world 15. You may wonder why during runtime, printf double check that you need to have two parameters. If the library makes such comparison, such check, you will take some additional check will be required, and thus reduce the efficiency. So for C program printf, they made the design decision not to do these checks. And okay, this another example. Okay, this is the full the whole programs. In these programs, okay, these are C programs. Okay, you may not know C program, but all these are very intuitive. This declare a string of 100 characters, an array of 100 characters. Scanf is a read the input. So he read from the input, the keyboard, a string and store it in T. And now I printed out T. So if this program is ran, okay, and the attacker can control this, suppose attacker is able to control what is input, then potentially if he put in the input of the string, he key in the string of hello world percentage D, okay, then extra information of this 15 will be printed out. So this is considered vulnerable. Okay, so if a program is vulnerable, in this case of this printf using so-called unsafe printf, the attacker might able to do this. The attacker might able to obtain more information. These are confidentiality loss, or cause the program to crash. Okay, this is execution integrity. Okay, and he may even modify the memory content using something called percentage n. So this is a memory integrity. For examples, suppose we are there is a web server here, and this one is a client. The program in the web server will ask for a client to enter a query, some query request. Okay, enter request. And for confirmations, this program, after writing the request, print it out, show it to the client, and ask for confirmation. Okay, confirmation. So this request here will be, supposingly the original intent is to show it here, this to copy this to here. Now suppose the this program here generate this reply using printf. If there is an unsafe printf here, the client potentially can put in using the percentage as and, okay, to cause the web server to print out more than intended. So this lead to confidentiality loss. The client may also using the percentage as to cause it to crash, Then that means this causing this web server to crash. Okay, so this become a denial of service attacks. It may even in the modify the contents. Okay, so this memory integrity. We will see more in the tutorial. To prevent this, there's a very simple prevention is to, at all costs, try to avoid writing program which taking only one parameter, and this parameter is a string. Okay, so try to write this version and these versions instead of this version. Let's look at another example. It's data representations. Different part of the programs may use different data representations. Such inconsistency could lead to vulnerability. Okay, let's give examples. Okay, string. There are many ways to represent string. String is different from array. String have variable length. Some string is long, some string are short. So let's look at this. This is a memory of the in the computers. Okay, let's look at this string. This string is stored here. This is a starting address of string, and this is the string. There are two ways to represent a string. Okay, one is called null terminated. Null terminated will do this. The length of the string is implicitly defined, okay, by the location of what we call a null characters. Okay. So the string will start from here. We keep going on until it hit the null characters. So here, this is the full string. Another way to represent it is called non-null representation. Have separately stored numbers. For example, in this case, 13, 15, I think 15, okay? So that means that the representation of the string will be an array plus a number. This number indicates what is the length of the string. So in this case, 15, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. Okay. So now during run times, we will know what is the length of the string. Okay. One advantage of a null terminated termination is that the length is implicitly implicitly given by the location of the null character, and we save 1 byte in representing the string. A system that use or a program that use both null and non-null definition may cause to okay. So let's look at let's look at one examples. Okay, of how this will cause problem. Let's suppose look at the certificate. A system that uses both null and no-null definition to verify the certificate may get confused. So for example, suppose I have a browser. The browser verified a certificate based on non-null termination. Okay, verify a certificate based on non-null termination, but he displayed the names based on null terminations. Okay, this will cause problem. Okay, let's look at that. Okay. Okay, consider, okay, this now, let us consider there's a vulnerable implementation of a browser that use this two different way to of a string representation. Now let's just consider attacks. Okay, this attacker, okay, he registered the foreign domain name and purchased a valid certificate with this name. Okay, so star.attacker.com. Then the attacker set up a spoof website, okay, of Luminous with these domain names, luminous.nus.edu.sg, followed by a null characters .attacker.com. Next, the attacker somehow is able to direct a victim to this spoof website. For example, he sent a phishing email to the attacker, to the victim, and victim accidentally click on this link, or using attacker control the physical layer, and somehow he can redirect the user to this spoof web server. The attacker's web server will present this certificate. Okay, maybe I using this one is easier. Okay, the attacker, so now this victim, instead of going to this Luminous, this should be Luminous, okay, is being directed to a spoof website. The attacker will present this certificate, okay, this certificate. And the victim browser, remember the browser verified the certificate using okay, this certificate is valid. Okay, it's valid, and the browser now look at this website, this domain name, and try to compare this domain name with star.attacker.com. The browser using non-null termination, and that when you do the comparison, you found that, oh yes, this actually belong to this using the regular expressions, and thus is valid. So this certificate is valid. Next, the browser would display this into the address bar. Okay, so this is what display as a browser, and there's an address bar here. So in this address bar, the browser use null termination. Because it's using null termination, what is being displayed here in the browser address bar will be this. So what will be displayed will be here. And because the certificate is valid, a padlock will be displayed. The user is very careful. The user, for example, the user, he know about the concept of a certificate authority and SSL and so on. So the user, he will look at this. He found that, oh, this is Luminous edu.sg, and there's a padlock here. That means that the certificate is valid. And now the user feels safe to go into the website and key in his password. But in fact, this is hosted in the spoof IBLE spoof website. So this attacks is real. I did not make it out. and there is a CVE number of this is in fact discovered in 2013. Let's look at another example. It's called UTF encoding. ASCII was designed for English characters, but later on, as more and more different languages join the internet, okay, so we need other representation for other languages, okay, and then this give to UTF-8 and UTF-16 and so on. UTF-8 represent a character in a slightly different way, and it trying to be backward compatible to ASCII. That means that even when you give him ASCII characters to a program that recognize UTF-8, it should able to recognize ASCII characters. So the representation is done in this way. Okay. UTF character can be 1 byte, 2 bytes, 3 bytes, and 4 bytes. How do I know that characters is 1 byte, 2 or 3 or 4? UTF use these conventions. We just look at the first bit. If the first bit is 0, means 1 byte. If the first bit is 1, the first 3 bits is 1, 1, 0, then this means 2 bytes. If it's a 1, 1, 1, 0, means 3 bytes, and 1, 1, 1, 1, 0 means 4 bytes. So now if it's a first bit is 0, then this will be treated as the ASCII characters. Okay, if it's of 2 bytes form, this will be used to we will concatenate all this. If it's 2 byte form, we'll just take these two, join them together, concatenate them together, and interpret it, and so on. So this will give 11 bits. This will be 16 bits for the X and 21 bits for the X. So under this representation is a unique representation. ASCII character can be represented in this way. This is the only way to represent ASCII characters. However, many implementation, this was originally defined in this way, but however, subsequently, many implementation accept multiple and local variant of ASCII characters. So, for example, ASCII characters of this 2F, that means a backslash, should be represented in this way. And many representation, they also have a 2 byte version. Okay, you do it this way. So that means you take all this and concatenate with this. This will give this. Or you take this 3, concatenate with this, you give this, and so on. So now backslash will have multiple representation. This represent backslash, this represent backslash, this represent backslash, and this also represent backslash. This will create some problems. Okay, so why backslash is so interesting? Okay, this is because in many file system, backslash is to use to represent the directory. So files, let's say index.html, this is the full file names. Okay, with the full path name of file, and this the backslash here indicate the subdirectories. Now consider programs, server-side programs, which we do this. The server-side program will request for file names, a string f from a client. And then he will do this. He will request a file names which represent as a string from a client. Then he will concatenate this string with the file name, okay, with the f here, and then read the file this file, you get this F, read this file and send the content to the client. The idea is that the web server will only read file in this directory only, in which directory, like home, the Alice directory. So this will create a problem. Why? Because an attacker, instead of honestly sending in the file names, sending a string of this form. If an attacker sends the string of this form to the server, which file will be read? Okay, the file to be read will be this. Okay, let me clear the string. Okay. Suppose the attacker sending this as a string F. Okay, the program will append it. You append this to here, and this will be dot slash CS2107 report .pdf. Okay. And the OS will interpret this as this file. Okay, this means go up one directory. That means I cancel this file. And this file is some other files in the Alice directory, which Alice originally don't want the client side to access. So by doing having this, we have a what we call privilege escalation again, okay, to allow the attacker to access file that he originally doesn't have privilege to access to. To prevent these attacks, one method is to do what we call input validations to make sure that ../ doesn't appear in the substring F. Okay, ../ doesn't appear here. Okay, so with input validation, we ask for the user to key in, read in the F and check that the string ../ okay, is not in F. Okay, if it's not there, if there, we quit. Otherwise, we'll append it and then make a system call to read the files. Now we further suppose that the system call in step 2 use a convention, a very usual convention in handle HTTP file, that the special character percentage indicate the corresponding byte value. For example, like home student percentage 61. Okay, percentage 61 will be replaced by the byte value 61, which is happen to be A in the ASCII representation. So now this check is not complete because ../ has many representation. ../ have this representation of this one, this one, this one, this one, and this one. Okay, if the user key in this or any of these 5, the file name will be decoded to this. So that's why it's because of this multiple representation create difficulty in doing input validation. Yet another example is IP address. Okay, IP address is 4 bytes. Okay, sometimes it's represented as a string, right? It can be many ways to represent this IP address. You can represent as a string using 4 integers or a single 32 bits integers. Okay. Now suppose that a program maintain a blacklist of IP address, and IP address is represented as 4 bytes. Okay. And this programmer, he wrote a subroutine BL blacklist, okay, that taking 4 inputs. Okay, this programmer, he wrote a program, okay, who had taken 4 parameters. Okay, these are the four bytes, each correspond to the 4 bytes in IP address. And the blacklist is stored as a 4 array of integers. Okay, so the blacklist is stored in this way: A, B, C, D. A is the first byte, B second byte, C third byte, and so on. Now the full program will be this. The program will get a string S from the user, okay, extract the 4 integers, okay, of the int types from string, and let them be A, B, C, D, and call the BL blacklist to check whether A, B, C, D is in the blacklist. If so, you will quit. If not, you will construct an IP address using this formula, okay, where IP is a 32 bits representation. And now we continue processing using this IP, which is a 32 bits represented bytes representations. 32 bits representations. So this one is a string representations. This is a integer representations, and then this is a third representations. It corresponds to this 1, 2, 3. So in this program, it involved these 3 representations. Okay. This will create problems. Okay, this will create problems, and what is these problems? That will be in the tutorial. How to prevent such attacks? Okay, typically the guideline is to use what we call canonical representation. Only use one representation, and do not trust the input from the user. When you get any input from the user, convert them to a standard canonical representations immediately and use it consistently throughout the whole programs. Buffer overflow. C and C++ allow programmer to manage the memory. They have something called pointer types. And the flexibility is very useful, but it's very prone to bugs. Furthermore, C and C++ do not do what we call bound checks. And this will have an efficiency, but also lead to vulnerabilities. Okay. Just look at these examples. So in these programs, we declare an array of size 5 and integer b. So in the memory, it's organized in this way. This is the array of size 5, 1, 2, 3, 4, 5, and this followed by the integer b. So in the program, first we assign b equals 0. Okay, when you print out what is the value of b, of course you get 0. And next, we assign a5 equal to 3. Where is a5? Here is a4, and here is a5. So now in C, okay, he did not do a bound check. He didn't check that this actually going out of the bound of the array. The C program will just use the formula to calculate the location of A5, which is here, and set this value to be 3. Set this value to be 3. And now if we print the value of a B, it will become 3. So it be change from 0 to 3. So this illustrates what we call buffer overflow, and sometimes known as buffer overrun. Okay, so in general, buffer overflow refers to a situation where the data are written beyond the boundary. Okay. Another example is string copies. String copies are copies. Let's use the examples. Okay, string copies. You copy the string in A2 into S1, S2 into S1. Okay. So now in this examples, S1, the size of S1 is 10. S1 is 10. So we have, so this S1 and this S2. And over here, we use the null terminated representation for strings. So string copy, when during runtime, we start to copy the string from here to S1. You get the first one and put it here, and the second one and store it here, and keep going until it hit end of the string, which is the null character, the null characters. So if it happens that the null characters occur after, let's say that the length of this 100, then 100 character will be copied over here. Okay. Although S1 is of size 10, so this will cause a buffer overrun. So you keep going on, go on, and go beyond it until you get the 100. So memory location beyond the boundary of S1 will be overwritten. Okay. So now in the situation that S2 is supplied by the attacker, that means attacker can inference the value of S2, then this will corrupt the memory beyond the S1. So in secure programming practice, instead of using string copy, which have did not give a bound or did not give a limit of a number of characters to be copied, we are advised to use string and copy, Here, we'll copy a string from S2 to S1, but with a bound of maximum of n characters, and most n characters will be copies. Also note that the improper usage of string copy can also lead to vulnerability, and we'll show this in the tutorial. A type of string buffer overflow is called stack smash, where when we are overflow into the stack. Okay, we understand more of this when we do the runtime stack, which is in the lecture 8. Right now, I briefly describe what's happening here. So whenever we call a function, like recursive function call, during runtime, we will call, the runtime environment will create an environment, okay, for the function. Okay, we make a lot of recursive function call. Whenever I make a new function call, runtime environment is created for the functions. So, like for example, in this case, foo have a local variable, and then during a runtime environment, we create a location, something to store the local variable foo, okay, which is 12 characters. There are also some important information to be stored here, which is a return address and other parameters. And all these are stored in the stack, on the stack. Now, in case that in the program we have a string copying bar to C2, and somehow bar can be inferenced, can be determined by the attacker. So if the attacker specified a string bar that is longer than 12, let's say 50, the length of this is 50, then 50 character will be copied into C12, array C, and cause a buffer overflow. That means here there's a 12 character here. When we try to the string copy, trying to copy bar to C, you will fill out this and then overflow to other important parameters. Okay. And now the consequences is significant because these are addressed. That means that you will point to the location of the next instruction to be executed. Okay. We'll mention more on this in the next lectures. integer overflows. Okay. So look at this code. A equal to 256 and A equal to A plus 2. And suppose A is an 8-bit integer, 8-bit integers. So A equal to 256, A equal to A plus 2. What is the value of A at this point? At this point, we know that it's 252, 254. But what about this? The value actually is 0. Okay. Why? Because it's implicit that if we are using A is a integer, the arithmetic actually is respect to modulo. So it's a modulo 256. Okay. So because A is a single byte, it's an 8-bit unsigned integer, so the maximum value is 256. Okay, so the range from 0 to 255, and all arithmetic addition multiplication will be done with respect to modulo 256. So 254 plus 2 is 256, 256 modulo 256 becomes 0. So in this case, we can see that A actually can be bigger than A plus 1. Okay, or A plus 2 can be in fact smaller than A. Okay, so this is so many programmer is not aware of this, and that this will cause a lot of problems. Okay, again, I leave it to a tutorial to look at such examples. Code injections. Okay. So a key concept in computer architecture is that a code can be, a program can be data, and data can also be programs. Okay. This is a very convenient, but it's also very confusing at some point, and many attacks inject malicious code as data. So now let's look at a scripting language. Okay. Scripting language is different from languages like C program. In C program, when we wrote a C program, we have to compile. Okay, you do a syntax check, and then we run it. Script language is worked differently. You can imagine that they are just a sequence of instructions. Okay, and then the interpreter, instead of compiler with interpreter will go to the first line, interpret it, carry out the instructions, go to the second line, third line, fourth line, and so on. They can also have a for loop and variables. And the script language, okay, somehow you allow the script to modify itself before it being interpreted. Okay, so in using this same example again, suppose I have a script language, we have a lot of lines here, and then we have an interpreter. Okay, interpreter read in this one and carry out the process. Okay, and this instruction may well be modifying this line. Okay, so this instruction go in, the instruction actually asks is a modified this line. So now you can see that this language actually can allow it to modify itself before it's been interpreted. Okay, so a very famous example is a SQL injection. SQL is a database query language. Okay, a database is actually a tables. So these are table, 2D tables, and every column corresponds to a attribute. Example, names, account, and weight. And every row is a record. Every row is a record. Okay, so this is attributes and then a record. The SQL query language, these are examples, okay, which do not go into detail, but it's quite intuitive. From here, we can guess what he's trying to do. He said that select this table, star mean the whole table, select star, select everything from client. This whole table is called client. This whole table is called client. Okay, select everything from client where the name equal to Bob. Okay, so okay, right now we don't have a name with a Bob. So you scan through this, find names where value is equal to Bob, and then the whole row will be output. Okay, in this case, maybe I should make this Bob 1, 2, 3, 6, 7. Okay. If the query script is select star from client where name equal to Bob, then this row will be reported. If you have two rows having the name Bob's 1, 2, 3, 6, 7, then two rows will be output. SQL allow some variables. For example, you can have a syntax like this: select star from client where name equal to user input, where user input is a variable, and this user input is supplied by the user. Okay. So for example, you let the user to key in the names, and then he will select the record where name equal to whatever specified by the user. Now in this example, let's consider an application where the names are secrets. So only the authentic entity who know the name can get the record. Okay, like in this example, every name is followed by some secret integers. So only the person who know the names were able to retrieve the record. He had to supply the correct names. Now, suppose that the attacker, instead of honestly keying the names, he keys something like that. He supplies this as the name. So the variable user input become this. Okay. And for the interpreter, okay, what they do is they just copy, okay, they just copy this into here. See, this is a language select star from client where name equal to user input. Okay, this is a variable. So for scripting language, they will put here, literally put it here. Okay, literally take this whole string and put it here. And now this result in this new SQL query, which read like this: select star from client where name equal to anything, or 1 equal to 1, or 1 equal to 1. Let me clean the, okay. So the query will become this one, okay, where select star from client where name equal to anything, okay, or 1 equal to 1. So this 2 is more like commented out, so it will be ignored. The interpreter will ignore this, the rest of this. 1 is always equal to 1. This is true. Okay, we don't know whether this is true or not, but this is all. So this whole thing, this whole predicate is always true. So now you will select every column because this is always true. You look through all columns to check whether this predicate is true. Then for all rows, this predicate indeed is true. So every row will be output. So the interpreter run above and return all the records. Okay. So code injection is not also limited to SQL injection. It's also possible to exploit buffer overflow to inject malicious code. Okay, we omit the detail. If you are interested, you can take a look into this. Undocumented access point. For debugging, many programmers inserted access point to inspect the state. Okay, for example, and by pressing certain combination of the key, the value of the variable will be displayed. For example, if you want to write you are writing a computer games, and then it's very difficult to reach the state. You have to play through the whole game to reach the state of having, let's say, experience point of 20,000. So for debugging purpose, it'll be convenient if you if we just, when we play the games, immediately we go to the state of having $20,000, 20,000 experience points. So many programmers to do the debugging will add in what we call the access point. When the game starts, by pressing a few buttons, immediately you gain 20,000 experience points. So this access point is useful in the debugging, but it may mistakenly remain in the final production system. Okay, so this provides a backdoor for the attackers. Okay, yeah. So if a attacker happen to know this backdoor, then of course the consequences is serious, because by pressing the few certain combination of key or trigger certain conditions, then you will get new information, or the program branch to some favorable stage. So this is also known as Easter egg. Okay, where Easter eggs is not malicious. Easter egg is benign and intentionally planted by the developer for fun. Okay, so one example is Google. Let's go to let me stop share and share the Google. Share the Google stream. Okay, so if we search for do barrel. Okay, so we have this. Okay, so this is 20 times. Oh, we couldn't. Okay, twice. No. Okay, so do a barrel roll. Okay, once. Okay, so this is what we call Easter egg. It's just purely just for fun. Okay. Of course, there are also backdoor planted by unhappy programmer. Okay, these are also called as a backdoor or logic bomb. Okay, this is also known as backdoor and or logic bombs. Okay, next one is much more complicated. It's called race condition, or also a special type of race condition is TOC/TOU, time of check and time of use. Time of checks, okay, time of checks or time of use. In general, race conditions occur when there are multiple processes trying to access a same piece of shared data, and the final outcome will depend on the sequence of accesses. Okay, let's look at this example with B and A. Okay, these are two parallel processes running concurrently. Okay, A will do this. A will first check whether the user have access right to read the file P. Okay, and if it's the user have the right, he will read the file. If user doesn't have the right, then it will hog. Okay, so you do this step, followed by this step. Now concurrently there's another process called B. He changed the file pointer. He changed the file pointers. Okay, so now the outcome will depend on where B perform this. Okay, let's look at this more detail. Okay, so we have two process A and B. Time of checks. Okay, this is A. A checks whether the process is authorized to read the files. Okay, suppose P now point to this non-sensitive file, and then you say, oh, it's authorized. If authorized, and after this checks, okay, after this checks, before A go to the accessing the file, B squeeze into the time and change the pointer to pointing to the sensitive files. Okay, at this point, A check whether the user is authorized, have the access right. Okay, of course the user have access right. Okay, now B come in, B change the files, the pointer pointing to a sensitive files. Now, during the time of use, now at this time, then A access the sensitive files. Okay. The user doesn't have the right to access a sensitive file, but because the B at this point of time switch it to the sensitive files, now A access it. Okay, so this is called a time of checks and time of use. The time of check, while we check, we are authorized to use it, but when we at the point that we need to use it, the user doesn't have the access right. Okay, during the time of checks, the user have access right, but okay, but after a while, okay, let me clear the thing. Okay, so there's a time of check. While checking, the user have the access right to get the files, but before we start to read, a process jump in and then change the files. Okay, and there is a race between A and B. If A read before B, then everything is safe. Okay, but if A read after B, then it's unsafe. So let's look at the more concrete examples. Okay, it's the same as this, but it's a much more concrete. Okay, so there's a system called access. Okay, who check whether the user who run the program has a permission to write to the file F. Okay, so access, he check whether the user have the access to the file, the right access. Okay, check whether the user have the right access to the file. And the check is done based on the process real UID. Okay, remember that every process have two ID, the real UID and the effective UID. Okay. Now, so he checked whether user have the access, have the right permission. Okay, suppose they have. Okay, it have permission is granted. Okay, if you have, then go to here. If it doesn't have permission, say unable to open the file. Suppose you have access permission, then you try to open the file and then perform operation on the files. So what is the race condition? Okay, so now we look at this case. Okay, so this program have the set UID on. That means that this program has elevated beverage. This program run as a root. This you can imagine that this is the bridge that I mentioned in the past two lectures. The bridge has a elevated beverage so as to allow the user to make some modification in the have some limited access to the sensitive files. So because this program but this part of the program, we don't allow the user to access sensitive files. Okay, so certain part of the program, we allow the user to access sensitive parts, but not this part. Okay, so because of that, this program do this check. Okay, you want to make sure that the user doesn't have right access to the files. So he make the library call, function call to check whether they have access. If have access, then open the files and do it. Okay. Now what happened is this. Okay, Bob. Okay, Bob is the user. He doesn't have a super user right. Okay, so Bob invoke this bridge. Okay, this program that have elevated beverage. Okay, and Bob want to access a sensitive file, which this one is a user calls CZ2107 grid. This one is not right. Bob doesn't have read-write access to this file, but Bob had read-write access to this file. Bob have this one, have access to this, but not this. Okay. So what Bob do with this? Bob will run the files, the elevated privilege files. Okay, so this file will be run. Okay, while during runtime, Bob supply the file name F. The file name F is this one where Bob have access to. Okay, so now you can imagine this is running times. Okay, this is a runtime. This is time. At this time, the program check the permission of the files. And indeed, Bob have write permission to this file. Because F is this one. Okay, this F is this file. Okay. Now, okay, so then at the same time, Bob also concurrently run this process. Okay, this process after the check has been done, this process immediately delete this file. This file is being deleted. Okay, and then create another link with the same file names, exactly the same as this, same name as this, but it's no longer a file, it's a link pointing to these sensitive files. Okay, the original file is being deleted, replaced by a link pointing to this. Okay. And now, at this point in time, the process who have elevated privilege, okay, want to write to the files. Okay, you look at the program here. Okay, he want to open these files. He want to open this file with these file names. Okay, and does he have the access? Yes, he have the access because this whole process has elevated privilege. So the OS granted access to this file, and then Bob now have great access to these files. So this is a time of check, and this is a time of use. And during this process, the Bobs, okay, change the state, okay, okay, and now he's causing this file to be read. Okay, so how do we prevent this? Okay, in the secure programming, so there are two ways to prevent this in secure programming. First one is this. Okay, it's a safe versions. Is that we use a file open. Okay, we open the files and we do not close the file, and we do all the operation here. At the end, then we close the files. Okay, after this file is open, the file will be locked. If the file is being locked, Bob is unable to modify it, and the file pointer or so-called file identifier is pointing to the same file throughout the whole process. Okay, so this is a safe versions. Another safe version is this. Okay, you remember why this program has elevated privilege, because certain part of program he really indeed require the elevated privilege to carry out certain processes. And this part of the process, this part of the program, in fact, is a doesn't need the elevated privilege. That's why we need to do this check. We need to do this check is to make sure that the user is accessing this part using his real UID. So a better way of doing it is that, okay, for this part, we keep the privilege as elevated. When we go to the certain part where the user doesn't need to have the privilege, we will lower the privilege, by using the set EUID. Okay, set UID, so lower it to the real UID, the normal user ID. After this is done, okay, when we required to have the program required to access sensitive data, then you restore the privilege to the root. Okay, so in fact, this is a recommended method. Defense and preventive measure. Okay, so many of the bugs are programming ignorance, okay, and it's very difficult to analyze a program to ensure it's bug free, okay. There isn't a foolproof method. Some of you may have heard of the halting problems, okay. So you want to check whether a program is doing certain functionality. It can be very difficult. It's a non-compute undecidable. Okay? But even that doesn't mean that we cannot do anything. We still can do our best, okay, to try to catch those errors. Input validation, okay. In many examples we have seen, okay, except the TOC, TOUs, the attack is carried out by attacker carefully fitting carefully crafted input to the system. Right, the printf, the bubble overflow, and SQL injections. This malicious input doesn't follow the expected format, like the input is too long, control characters, contains negative number extra. Okay. So one way to prevent this is to carry out input validation to check that input indeed follow the expected formats. So there are many ways of checking. So one way to do a whitelist. Okay. So we have a list of items that's known to be benign. We only allow them to pass through, or a blacklist. There are bad choices and want to cancel, remove them. As we see from the example of dot stress, okay, in the dot stress example last week we have done it. It's also in some sense is a blacklist. It's a blacklist. You can see that it's very difficult to be complete. Okay, so it's very difficult to design a filter that is complete and accept all legitimate input. Okay, this one is not required, it's optional, and I leave it. If you're interested, you can take a look in this one. Okay. And input validation. Where should we apply input validation? Okay, this is very common in web programming. In web programming, we have a browser, and a browser we have some JavaScript or we have some program running here. Okay, and the browser will, when the user will key in the input, okay, and then this will be sent to the web server, and web server will, for example, this is an SQL query. Okay, this SQL query, then the input of SQL query can be is entered in the browser, sent to the web browser server, and then sent to the SQL server. Now, where should the input validation done? Should be the input validation done here, or input validation done here? Okay, you can see that if the input validation is done here, the user, because the user the attacker control the whole browser, okay, it can also bypass this validation mechanism. Okay, you can immediately, you can look at the code, okay, bypass the code, okay, and immediately send the SQL, the query directly to the filter, to the web server without being filtered. Okay, so many attacks is of this form. Okay, where we will talk about this again in web security. One way to prevent the printf is not to use it altogether. Okay, so like printf, just ignore, just don't use these functions. And string copy, don't use this. Always use a string and copies and access. Okay, so these are so-called safe function, which has to be avoided at all costs. Okay, so for string copy, try to use string and copies, and trying to avoid string f, printf, where f is a variable that can be supplied by the user. bound check and type safety. You probably have heard that Java and Pascal perform bound checking. If all programs are implemented using Java or Pascal, so we will eliminate most of the buffer overflow. Okay, so and what do they do for Java and Pascal? The so-called bound check. They every time when assignment is carried out, what actually being carried out is that they will do a check. They'll check whether I is smaller than bound or I is bigger than the upper bound, and then he assign. In contrast, C and C++ do not do the bound checks. Okay, because he do not do the bound checks, it's faster. He don't have to do this too, and because Java had to do bound check, that's why it's slower. Many of the no vulnerability are due to buffer overflow. Okay, and if you use bound check, all this can be prevented. You can go to this website to see how many. You just search for buffer overflow and see how many CVE is related to buffer overflow. Okay, string. Okay, type safety. Okay, some programming languages carry out type safety to make sure that the operation are of the same types. For example, like A equal to B. Okay, if A is 8 bit, B is 64 bits, if you take A equal to B, then potentially you will have an integer overflow problems. So some programming languages also do this check. You want to assign something, you will make sure that these two are of the same types. Canary and the memory protections. So for buffer overflow, okay, if you use the string copy, if you use the string copies for to cause a buffer overflow, the data had to be copy in this way, okay, to keep writing in this way, okay. So that's why buffer overflow sometimes is also called buffer overrun, okay. So the overflow have to, if the attacker want to modify this address, he has to modify everything before it. Okay, remember string copy, right? Okay, string copy S2 to S2 to S1. Okay, this S1. And suppose this is the memory of S1, and these are sensitive data. To do a string copies, okay, to do a buffer overflow, we have to copy from here, 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 copy. Okay, and hit the sensitive data. Okay, so everything around here will be modified, had to be modified. So canaries will do this. Okay, you will the compiler or during runtime they will insert some value called canary in this location, in front of a sensitive data. Okay, these are secret value. So when very frequently during the runtime, they will check whether this value has been modified. If this value is being modified, then exception is true, and then the machine will crash. So now, if we want to use buffer overflow to write into the sensitive, then this can be detected. Okay, but this is still not a foolproof method. Why? Because if the attacker happen to know the secret value, it's still able to overflow into the sensitive region without being detected. So we will talk about this again when we do lecture 8. Okay, then for a lot of these attacks, the attacker need to know the memory locations, the location where store the memory. So there's one defensive mechanism is to use so-called memory randomizations, where the memory space layout is randomized. Using different runtime, the memory location is different. Okay, another way to do it is by code inspection. That means a manually check or use automated check. For example, taining analysis. Tain analysis is to keep track of all the variables that potentially can be influenced by the user. Okay, so the tain analysis can be static or can be runtimes. Okay, and testing, of course, we can do a lot of testing using whiteboard testing. In whiteboard testing, the tester have access to the code, black box, gray box, or something called fuzzing, randomly feed in the input, different input, until the program crash. Okay, this apply to the TOCTO, the TOCTOU, time of check, time of use. Okay, so when you write an elevated while writing a program, you will try to lower the privilege when the part of the program doesn't require privilege access. Okay, you only allow it when necessary. Okay, so this is called principle of least privilege. So when a vulnerability is discovered, okay, the code had to be fixed, and then the revised version is tested, and the patch is made public. Okay, so let's look at this card. Okay, so program has many bugs. Okay, so we need some time to find it. If it is found, then we need to release the patch. Okay, and very interestingly, this someone is this pattern is often observed. Okay, this is the time. This is a number of intrusion. Number of time the vulnerability is being exploited by the user. When it's discovered, there are very little, very little intrusion. But when it's disclosed, then okay, during this time, maybe the person will discover, share with a few people, and thus the number of intrusion increase. But when it's disclosed, then the number of intrusion increase. Why? Because when it's disclosed, then more people will know about the vulnerability, and then you have of course you have more intrusions. And then when the patch release, it will go up because not machine is patched immediately, and then it will go down after it's been patched. Okay, so this is a typical life cycle of the number of intrusions. Okay, it's crucial to apply the patch timely. Okay, so although seem easy, applying patch is not straightforward. For critical system, it's not wise to apply the patch immediately because it may crash a system. Okay, so the patch may affect the application and affect the usability. Okay, patch management is the field of study, and there's a guide on how to do a patch. Okay, with this, I end these lectures, and next lecture we'll talk about the architectures and then the web security, and that will be our last lectures.